Hi everyone, we are back and we are going to go through our Pset 1. Oops. Let's go ahead and maximize this. Put it back up here. Let's minimize just for a little bit. Let me get my pen. We're going to go through our Pset 1 solution videos. So let's go ahead and get started. What is wrong with the graph below? Explain in very thorough detail. So first thing we can see here with this graph is, well, what are we looking at? What are our axes labels? Well, there are none. So we don't have any axes labels here. We don't have any axes labels here. We don't know what the units are. We don't know what's being plotted. There's no caption, and there's no description of the caption as well. So that's very, very, very bad. Color scheme is okay. So blue, red, purple. But what is blue? What is red? What is purple? So we don't have basically, a figure legend as well. There's not error bars on this plot, which basically tell me, again, we want to see or at least have some description of error bars. So very, very, very bad plot. Also, you can kind of see this is definitely like a screenshot. The resolution is very poor. These are not the plots that we want to produce in this class. So basically be sure to kind of follow the guidelines that we kind of described previously. All right, reread the expert from this from a lab report from a student. Do you see any issues with the term accuracy, resolution, precision, and sensitivity? Rewrite and correct if it needs to be corrected. So we've measured the mass of a DSC sample using microbalance. We followed an average value of this. We measured the mass 183 times, good, n greater than 30, so that means large sample size. Observed a deviation of 2 milligrams, despite the fact that the microbalance can measure masses as small as 0.5 micrograms. The theoretical value of the DSC sample was reported to be 4.98 milligrams. Thus, we have a very, so let's see, theoretical value was this. Thus, we have a very precise measurement, but the accuracy, resolution, and sensitivity is all relatively poor. So very precise. So precise means that the measurements, basically, you're getting, it's the deviation effectively in your measurements. So like if I'm measuring 5 milligrams, 5.1, 4.99, this would be something that would have very, very high precision. But we're saying that we have deviation of 2 milligrams. So we're getting plus or minuses of 2 milligrams, even though our microvalence has very, very high resolution and very, very high sensitivity. So actually we have very, very poor precision. The accuracy is okay because the average is this and the theoretical value supposedly is going to be this. So we're actually okay on accuracy. We have very, very poor precision, and then we have very, very high sensitivity and resolution. All right. What's wrong with this graph? This is looking pretty good. We have our labels here. We have a pretty nice caption here. Stress. Again, figure legend shows what the graphs that we're looking at. Again, resolution can be improved, but that's actually my issue. Don't want to start off with just like displays. So this can be improved here. Again, write full sentences, capitalize everything. But again, and this can be honestly expanded a little bit. But overall, this is a pretty good graph for what it's trying to report. So decent job. I would actually frame this a little bit, but we're using the dead space, which is pretty good. So yeah, this is not a horrible graph. We can improve, but this is pretty good. All right. Finally, I'm working with 3 different universal testing systems. System A can measure forces between this and this and can resolve this. B can between 1 and this and can resolve this. 0.1 kilonewtons. Let's go ahead. Actually, I'm going to erase this real quick here. Hopefully you can. Nope. I need to just... let's see. I'm trying to pull up my drawing template, but it's not working. System C can measure between 100 this and can resolve approximately 10 kilonewtons. I must trust undergraduate students measure the pull-out strength of a screw from bone sample, which should be this. So this should be the true value, even though there's really no true value. My students report that after 89 measurements, they found out that system A measured a maximum value of basically 95.4 an average, or actually an maximum value of this, a minimum value of this. B maximum was this. And this, I assume in kilonewtons respectively. For system C, the maximum value was this, and the minimum was this. Write a description of the 3 systems and and assess their accuracy, precision, sensitivity, and resolution. Be thorough in your response. So if we want to look at kind of sensitivity and resolution, resolution is going to be basically about what can a system actually resolve or measure. So system B can do 5 newtons. 0.1 kilonewtons is going to be, let's just kind of keep it, so let's see, 0.1, 1, 2, 3. So that's going to be 100 newtons here. And then system C can have that. So system A is the worst in terms of resolution and sensitivity. System B has the highest resolution. System C, system C is the worst because it's 10 kilonewtons. So let's go ahead and A, B, C, 5 Newton, and this is 10, 1, 2, 3 Newton. Also, doesn't have the range essentially to measure these values. So this would have the highest resolution, highest sensitivity. This would be the worst. So boom, boom. It should measure 89 kilonewtons. So let's look at some of the measurements that we're seeing here. In terms of accuracy, it looks like system B is the best because we're basically right on that value of around 89. So this is looking good. So system B is the most accurate as well. Also, it looks to have the most precision as well. So precision-wise, we can see that there's not much deviation here. This is about a 50 kilonewton deviation here. Here we have about a 15 kilonewton deviation for A. So again, we're getting significant deviations in between measurements. So system B is definitely the one we want to look at. Another interesting thing here we can see, we're actually getting measurements for system C that we shouldn't really even be able to measure according to our machine. So that's a little bit odd as well that you can kind of point out and dive into there. But yeah, that's pretty much it. So go through and make sure we know those definitions, and that is our problem set 1 done. So we'll see you in the next video. Thanks. Bye.